I'll write above it what I was doing. This is T of V1. This is T of V2. This is T of V3. Coordinate vector of it, T of V4. So I'm saying this is V1, this is V2, this is V3, this is V4.
Why use the brackets rather than
Because I'm talking about the coordinate vectors. Coordinate vectors. What is the coordinate vector of 0 with respect to the... So gamma's 1, 2, 3 dimensional. So we're going to have a 3 by 4 matrix. 0, 0, 0. I'll get us started. What's the coordinate vector of 1? No, it's 1, 0, 0. Because I have 1 copy of 1, 0 copies of x, 0 copies of x squared. This one, I have two copies of x. I've got 0 times 1 plus 2 times x plus 0 times x squared. That's 2x, right? That makes this 0, 2, 0. This one, I would have 0 copies of 1, 0 copies of x, 3 copies of x squared, right? What'd you say?
I was just saying, I understand what you said.
0 what? 0, 0, 3, right. And there you go. That is the matrix of the derivative map with respect to the choice of bases beta, gamma. If you choose different basis, you get different matrices. In the problem of coordinate change, one of the problems of coordinate change is to understand how that matrix changes if you make a change in the coordinate choice of coordinates. But there's also a more basic question to understand. How does the coordinate vectors of a vector change if you choose a different basis, right? Did you guys cover this in linear? You might not have. It's a pain to cover this topic. It's a little bit technical. It's kind of, this will wear students down, especially at the time of the semester you hit it. It's very tempting to and I don't know, not everybody enjoys this topic as much as I do, but anyway, there is another way to find this matrix, and that's to use the implicit definition, all right? Let me show you the same example, but a different way. I'm going to use this picture to do the same example. Oh, there we go. No, other way. So if we So here we've got what? We had P3, right? We have P2 over here, right? We have our mapping, our mysterious, well, we know what it is, derivative mapping, right? So what you do, and I'm going to use the same basis, beta and gamma, that we had, all right? So what you have to do is you have to follow an arbitrary vector in the domain. In this case, that would be a plus bx plus cx squared plus dx cubed. I'm going to call that v. You could call it f of x if you wanted. I'm going to call it v. Right? So what's tv over here? It's b plus 2cx plus what? 3dx squared, right? So what's the coordinate vector? with respect to basis beta of V.
1x, x squared is
There's no x's in the coordinate vector. It has to be a column vector with just numbers in it. Your choices are
A, B, C,
A, B, C, D, right? Oh yeah, and that's exactly it, A, B, C, D. Because, yeah, we made it match like that, A, B, C, D. Great. What's the coordinate vector over here of TV with respect to the gamma basis?
B, 2C, 3D.
Yeah, B, 2C, 3D. Very good. Now, to find the matrix, all you have to do is basically say, okay, what we need is we need some mystery matrix, which we can tell has to be a 3 by 4 matrix, such that this matrix times A, B, C, D is equal to B, 2C, 3D. And then to calculate the matrix, you just fill in the blanks. Like I say, okay, I need this, the first row, I have to put, 4 entries.
Yeah, it has to be 0, 1, 0, 0.
Exactly, because I have to get B
You
back.
can only get B. And then the second row should be, yeah,
Yeah, 0, 0, 2, 0.
and that one should be 3 at the end.
Yeah. I mean, it's going to be the same thing again, right? And that right there, whatever that works out to be, that is the matrix of linear transformation with respect to these non-standard bases. So you guys, probably did not do this, no. And that's fine. But.
I saw a flashing light outside.
Oh, that was. Now here's the cool thing. Well, there's many cool things, but so for an abstract linear transformation, you can again judge whether it is one-to-one or onto in terms of subspaces of the map, right? You have kernel T. Kernel of T is V and V, such that T of V is 0. Sounds like that train's about to come in the building, So the kernel, what's that? What's that? Oh, it's a plane?
The train's never been. Because it sounds like it's right.
That's definitely not a train.
Well, that's very disturbing then. Is there an airport here?
It's one in Marie.
Maybe some big helicopter down on it. But I feel like you hear it.
It's not like a tornado warning or anything right now, is there? Yeah.
No, you hear it. All our phones would be ringing.
Ah, cool. So you can talk about the kernel of T, right? And if the linear transformation is one-to-one, if and only if the kernel is just 0, right? You can talk about the range of T or the image of T. What's that? That's T of V, right? And so if the mapping is onto, if and only if the image is the whole of W, right? And there's still a rank nullity theorem. The rank nullity theorem, in this case, says that the dimension of the kernel of T plus the dimension of the image of T has to be equal to the dimension of V. But there's other things, like, the thing that I think is perhaps interesting is this, the dimension of the kernel of T is equal to the dimension of the null space of the matrix. the dimension of the range is, guess what? The dimension of the column space of the matrix. So there's something very interesting here in a sense, because there's no basis on the left-hand side of this equation I just wrote, right? But there's a choice of basis beta and basis gamma on the other side. So what I'm saying is it doesn't matter what choice of basis you make, it captures sort of the essence of the linear transformation, how it works. And so you can calculate the dimension of the kernel and the dimension of the range just by taking a snapshot of the linear transformation with respect to this one pair of bases. This is what my linear algebra teacher, graduate linear algebra teacher, used to always talk about. He'd be like, the matrix of linear transformation is a picture. It's a snapshot of it. He'd always talk about snapshots. But anyway. Okay, so part of the reason, so I'm not going to talk to you guys about coordinate change today, all right? Maybe next time we'll talk about it. I have to think about my life and decide whether or not it's actually worth it for us. But this actually, a vector space, is your first example of a manifold. And the reason is this. The coordinate map, right? It actually is a chart on the whole vector space. It gives you a one-to-one correspondence with Rn. And that's a linear correspondence, which means it's smooth, right? If you take a different basis and you take a different coordinate chart, when you compose the coordinate charts, when you basically look at those transition functions we talked about in the previous class, the transition functions are actually multiplication by an invertible matrix. That's smooth. So vector spaces, in some sense, it's your first example of a manifold where the coordinates are actually interesting and they are useful to analyze things on the vector space. So in contrast, abstract manifolds, we can't find one coordinate chart that covers the whole space necessarily, right? Like with the sphere we saw. And also, the patch that we were looking at is the other direction. It's going from Rn up to the manifold, whereas here, the coordinate chart is going from the vector space down to Rn. So it's a chart. The inverse of a patch is a chart. We found some of those last time, too, when we were looking at examples. But anyway, I'll try to pick up here next time. I should actually show you guys coordinate change, because I think we've got this far into it. I owe it to you. But I think you'll find, I'm going to actually give you some more examples where you find the abstract matrix. I think you'll find it pretty enjoyable. Once you understand the picture thing, what do you guys think? The picture thing easier? My students usually like the picture thing more than the... Yeah.
I'm not used to working with them, so.
Oh, no doubt.